This is a rocket called Mach 2. I named it that because the rocket's maximum speed is Mach 2. My goal is to test new control systems, a new GPS chip, and fix a telemetry problem that I've had for years. Pulling 32G off the pad with an L1000 rocket motor hitting Mach 2 should be a breeze. But I cut some corners on this project, so for the rocket, surviving the flight will not be easy.
Uh-oh, that was bad.
Oh.
There's a pop. Okay.
This rocket wasn't supposed to exist, and in fact it didn't until 4 days before launch. I threw it together from spare parts I had lying around, like this L1000 rocket motor from an old roll control test series. These motors are ready to fire right out of the box, and it's time to put this one to good use, along with a nose cone, an extra flight computer, and some servos. Maybe good use isn't very accurate, it's called Mach 2. Maybe we're just putting it to use. I'm 3D printing the fins out of PLA, and I went with 100% infill and 6 wall layers. It's overkill, but if this rocket fails, I don't want the fins to be the reason. There's a small cutout for a servo that I'll use to control a tab on the trailing edge of the fin, and I'll use this to steer the roll axis of the rocket. Interestingly, it's only on one side of the rocket, which means we're controlling this thing asymmetrically. If we apply a force here without a counterforce on the other side, aren't we technically pitching the rocket, not just rolling it? Yes. But also no. Hold that thought. To keep the surface smooth, I removed the servo connector and soldered the leads into a PWM extension cable. Then I tacked it all down into the fins with CA. I then epoxied the fin can onto the motor and added the 3D printed boat tail to the back, which will help reduce base drag. I 3D printed rail guides to attach it to the launch pad and epoxied those to the fin can. Then, after sanding off the label, I prepped the forward end of the motor. First, I drilled 2 holes in the forward closure to attach parachute lines, and then I filled this top section with epoxy. This little hole is usually open because the L1000 motor has a delay grain at the top. This is a section of propellant that burns very slowly from bottom to top, and when it hits the top, it ignites whatever's up there. Usually it's black powder, which is used to deploy parachutes. The thing is, that delay time is only 18 seconds. We can shorten the time by drilling into it, but we can't lengthen it, and our time to apogee is currently predicted at 26 seconds. And it's really bad for us to pop parachutes early. It's not good for us to pop parachutes early. All right. To finish off the booster, we need to do a few things. First, this servo cable is loose, so I'll tack it down with some CA glue. Then we'll do some freeform composites work. I rolled out a sheet of Mylar because I knew it'd get messy, then I mixed a batch of expired laminating epoxy and degassed it. The problem with a servo cutout is that the area around it becomes weak. This whole bottom section is only supported on the edge of the fin, and the 3D printed layer lines make that even weaker. In my previous rockets with 3D printed fins and servo cutouts, a hard enough landing usually broke the fins around this area. So my plan is to do a carbon fiber layup on this section to increase stiffness, but it brings us back to the question of why we have this single servo here at all. It's asymmetric control, and that should lead to stability issues, right? If I spin myself in a chair, I can control my spin rate by getting bigger or smaller, and it's because of the conservation of angular momentum. The momentum that I have here is the same that I have with my legs in. What's changing is my mass moment of inertia. For a rigid body, the equation for angular momentum is moment of inertia times angular velocity, and since momentum is conserved, that number is fixed. It can't change. When I pull my legs in, my moment of inertia goes down, and the only thing that can change now is my angular velocity. It has to go up because momentum is conserved. And the smaller I am on my rotational axis, the easier it is for me to rotate. I'm so dizzy. I'm on take 5. It's really getting to me. A rocket is no different. Since the roll axis is the smallest, it's far easier to rotate about the roll axis than it is to pitch or yaw, and the math tells us just how much. If we assume the rocket is a solid cylinder, which it's not, but it's close, the equation for the roll axis MOI is 1/2 mr squared. If the rocket is 5 kilograms with a 27mm radius, our MOI is 0.0018 kilogram meters squared. The math for the pitch axis is a bit more complicated, but when we add the length of the rocket at 1.5 meters, the MOI on the pitch is 0.626 kilogram meters squared. That is over 400 times larger. It's 400 times harder to rotate the pitch axis than it is to to rotate the roll axis. So yes, asymmetric control does have an effect on the pitch axis, it's just so tiny that it doesn't matter. This asymmetric setup has worked beautifully on past flights, where a single roll tab on the trailing edge of the fin has produced a stable roll axis with virtually no effect on pitch or yaw. So with that covered, let's get back to the rocket. I want a layer of carbon fiber around this area for extra strength, but since those leads are exposed, I'll toss 2 layers of fiberglass down first. Carbon fiber is conductive, as we learned the hard way in this video, and that's what those fiberglass layers are about. So I laid down the carbon fiber after, then added 1 more layer of 2-ounce fiberglass to smooth it out on the surface. These fins are obviously super thick to accommodate the embedded servo, so we should try to get performance back in other areas. That's why I decided to attach the fins directly to the rocket motor, rather than using a separate airframe tube. It means this rocket is single use, but it turns the build into something called sub-minimum diameter. Can I go on like a really quick rant? Okay, so in hobby rocketry, we have terms to describe how much space the propulsion system takes up. It's not thrust to weight ratio, it's how much physical space the motor occupies. This is a rocket I built a few years ago called Avalanche. It has a 38mm motor mount in the back, but the outer diameter is 75mm. The space in between the motor tube and the outer tube is just wasted. It's just empty. So what if I want more performance from my rocket? We can get that with something like this. Send it. This is my level 3 certification rocket I built a few years ago. It's 98mm in diameter and the motor fits right into the airframe. There's no motor mount here, it's just airframe. We're filling all the space inside the airframe with as much motor as possible. In rocketry, we call this minimum diameter because the airframe couldn't possibly be smaller. The motor's occupying all that internal space. And that's what minimum means, the smallest possible. I mean, the airframe can't get smaller here, right? Except, of course it can. What if the airframe is the rocket motor case? If the fins are attached directly to the motor case, that is the actual minimum possible diameter. It's as large as it could be. There's no diameter that can be smaller than this. This is the minimum diameter. But we already named this one minimum diameter, so we call this one sub-minimum. You telling me this minimum is Sorry. In what world is it possible to be sub-minimum? That doesn't make any sense. Minimum, by definition, is the smallest possible. It's a non-gradable absolute. You're either minimum or you're not. You can't be below it. A sub-minimum diameter doesn't exist. If it's sub-minimum, it's 0. I mean, am I crazy? Don't answer that. I'd like to propose that we call this true minimum because it is the smallest that it could possibly be, and we call this something like conformal minimum or sleeved minimum. Thank you for listening to my rant. Let's get back to it. Mach 2 is a true minimum diameter rocket because we're attaching fins directly to the motor case. None of this sub-minimum nonsense. After the layup on the fins, I used 2 layers of 2-ounce fiberglass to cover up the servo cable on the side, then a generous amount of epoxy to attach the airframe section on the forward end of the motor, completely ruining everything that I just said about this rocket being a true minimum diameter build. Now, it's an unholy mishmash of both. I drilled a hole through this tube to pop the servo cable inside, then added a few more layers of 2-ounce fiberglass with an excess of epoxy to seal it up and smooth out the surface. This stuff will take a little while to harden, and we've got to kill some time, so let me tell you about the sponsor for today's video. This video is sponsored by Novium, which are the makers of this cool hover pen. This thing is the Hover Pen Interstellar, and it sits at a 23.5-degree angle in its magnetic mount, which is the exact same angle as the Earth's tilt. Novium create high-end, innovative writing products, and if the Hover Pen Interstellar isn't your speed, maybe the Hover Pen Future is what you'd like, and this one sits at a 60-degree angle. These pens hang in their mounts using magnets, and all around they're designed with inspiration from the cosmos, so they make great gifts for the space nerds in your life. And if you're looking for surfaces to write on, look no further than the Novium Notebook, which is among the many accessories they sell, like these ink refills. Each pen comes with an ink refill, and these things are so nice, you're going to want to fill that ink back up. All these pens come in various colors, so if what you're seeing on screen isn't your speed, there's probably an option that'll fit. And there's even a premium version of the Hover Pen Interstellar, which has a meteorite fragment embedded in the tip. You can get free shipping to most countries, and if you order soon, it should arrive in time for the holidays. So if you're looking to give these things a try, you can use my code BPS at checkout. You can also hit that link in the description or use the QR code here, and that'll get you 15% off all hover pens for the next 72 hours. Once again, these make great gifts, and thank you so much to Novium for sponsoring this video. Now let's get back to it. With the addition of a set of upper rail guides, the booster section is complete, so I brought it outside to give it a coat of white paint. And now it's time to focus on the upper section of the rocket, which will house cameras and avionics. I'll cut out a section of 54mm fiberglass tube for this, then add a coupler section so it can fit into the booster. Then I'll make a bulkhead to pass through wires and attach chute lines. These wires are PWM cables for the roll servo, the leads for the parachute deployment charge, and the bulkhead gets epoxied in after. Next, I added the main onboard camera, a deconstructed GoPro Hero 10. I've got a whole video on how this process works, but here's a quick rundown. The GoPros offer this 4K 120 frames per second footage that I'm looking for, and so I buy cheaper versions and tear them apart to fit them into small spaces. I thermal paste a block of aluminum on there to act as a heat sink and prevent them from overheating, and then I embed them in the rocket with a protective coat of resin around the sensor element outside. Once this was done, I brought the tube outside and I made an even larger cutout. I mean, this one is huge, and so we need to talk about why I'm doing it, but first, let's talk avionics. The main flight computer is Ava, the board I designed back in 2020 with the goal of controlling every single thing I build, which so far has been working great. I used to make a new flight computer for almost every one of my projects, but now look at all the rockets that have flown with this thing. Ava, 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 Ava. You know when you say a word too much and then it starts to sound weird? Ava will be in charge of deploying parachutes, controlling the roll axis servo, reading GPS coordinates, and then sending telemetry back to the ground station so we can find the rocket after it lands. The projected apogee is 5 kilometers, and I will not be able to see that thing so high in the air. We need to get those coordinates. Ava will get mounted to this sled with a 2-cell LiPo for power, and the GoPro will be tied to one of Ava's high current MOSFETs to turn it on right before launch wirelessly. For the primary GPS, I'll use a helical antenna loosely placed in the nose cone. Then I've got a secondary GPS embedded near the tip of the nose. This is a new unit I'm trying out, and I'm hopeful it'll help us get GPS speed and altitude above some of the typical limitations of usual GPS chips. I'm not 100% sure if this chip will work, which is why I'm testing it on smaller rockets, and until I've gathered more data, that'll have to wait for a later video. The last part of Ava's job is telemetry, which will be sent out using an RFD 900 radio. These work around 915 megahertz, and in theory they should work super well. But something isn't right with them, and it hasn't been for like a long time. Telemetry is something I have always struggled with, for years. When I started flying really high power stuff in 2021, I began consistently encountering two kinds of errors. When Lumineer launched, after 4 kilometers telemetry was lost, and since that moment, it has been a consistently mixed bag. The next big rocket, Send It, had a great telemetry link, but couldn't get GPS signal. The next 7 rockets used the exact same GPS chips and telemetry radios, and each time it was like a total coin toss. Between GPS and telemetry, one of them was always performing poorly, if not both of them. For a while, I thought this had to do with where I was launching, like the physical location. I brought a bunch of equipment out to FAR to try and prove this theory and analyze the RF spectrum out there, but I couldn't find anything conclusive. There was never any real data to support that theory. While the GPS and radio chipsets across these rockets remained the same, the only thing that really changed was the antennas. But I'm only using antennas that are listed to work with the frequencies I'm on, and some of these antennas are stock. Like these antennas right here ship with the RFD 900. I can't imagine that they would send me antennas that don't work with the radio in the box when it's brand new. But this is one of the last things I haven't tested for, so let's change that. This device is called a Vector Network Analyzer, and after calibrating it, I'll use the VNA to analyze the effectiveness of the only thing I have been changing. When I buy new antennas, I look for a few traits. Things like gain, directivity, size, and of course bandwidth. You want an antenna that is tuned to the bandwidth you're trying to work on. My telemetry radios work at 915 megahertz, so let's plug in a good antenna and see how it looks. The diagram here is called a Smith chart, and it looks complicated, so let's ignore all of these white lines and just focus on the blue one for now, which represents the standing wave ratio, or SWR. When you pump energy into a radio, the hope is that every watt you push into the antenna is radiated outward, and nothing comes back into the radio. If your antenna's good, all that energy leaves as radio waves, and if your antenna sucks, some of it's going to get reflected back in, and if enough of that gets reflected, it can actually damage the radio. But a reflected wave from something like an impedance mismatch or poorly tuned antenna can mess with the signal we're trying to send. The resulting standing wave, or composite wave, will be more or less powerful than the signal we originally originally sent down the line, and SWR is a measure of the ratio between these two voltages. The more these waves don't match up, the higher that ratio is. 1.5 to 1 is pretty good, 2.5 to 1 is okay but not great. After about 3.5 to 1, your antenna is pretty bad and you might start damaging the radio. This ratio changes with frequency too. Antennas are tuned to work at specific frequencies best, so there's a sweet spot where this ratio will be really close to 1. In this case, the VNA is showing between 800 MHz and 1.1 GHz, so 915 is a little to the left of center. The antenna we've got hooked up here is tuned to 915, and look at that, with the marker at 915, we've got an SWR at 1.073. That's really good. The other line to look at is the green one, which is a trace against the goofy-looking Smith chart. The way to read this is that we want the green line as close to center as possible. The left side represents a short circuit in the antenna, and the right side represents an open circuit. Up and down on the plot represent too much inductance and too much capacitance. And our green line, with the marker at 915 MHz, threads the needle between all of these, right near the center. Now let's look at the antenna that ships with the radio. This one should work great. I mean, it's sold as a set, but our SWR has jumped up to 1.6, and the Smith plot shows us the antenna isn't tuned well. If I move the cursor, this one would actually work a little better if we were at like 895 MHz. Here's a quarter wave antenna, which is even worse. The SWR and Smith chart look terrible around 915 MHz, where it's supposed to work, but it would actually work a lot better near 970. And here's another quarter wave that's a little better, with an SWR of 2.5 and an antenna that's just a little bit capacitive. And finally, now let's go back to the original antenna with that really low SWR and great looking Smith chart. This tells us the antenna is efficient, that it will work well, and the Smith chart tells us that the impedance is matched. It's fascinating to me that the antennas that literally ship with the radio perform so poorly, but it starts to explain all of my intermittent issues. I had been trusting that the antennas I bought would work as advertised, and I mean, they're rated for 915 MHz, why would they lie like that? This is the internet. You're not supposed to lie. The same bummer is true for the GPS antennas I use, though the plots look a little different. GPS, or more accurately GNSS, is spread across a wide range of frequencies between 1.1 and 1.6 GHz, so we can't just tune the antenna for one frequency, we have to spread it out. The helical antenna has a very bumpy response, with an SWR bouncing between 1.8 and 2, and a Smith chart showing a spiraling trace close to the ideal match. I found that many of the GPS antennas I had been using looked like garbage on the VNA, just like the telemetry antennas. It's no wonder I've had so much trouble. I've just been using bad antennas. So for Mach 2, I made sure to select antennas that were tuned really well for both telemetry and GPS. And just as a backup, I also placed a radio beacon tracker attached to the parachute. And this will help us find the rocket if we're in like a really worst case scenario where the avionics die. And with that, I charged up the batteries, popped in some shear pins, loaded the avionics. We forgot to talk about the hole in the side. All right. Hear me out. For a long time, I've wanted a third-person shot of a rocket at apogee, something like this Up Aerospace shot from a few years ago. I've tried versions of this before, but I never give the design enough time or effort to actually work, and that's what happened here. I created a tiny camera payload designed to shoot out at apogee and get a shot of drogue deployment, and I managed a few successful deployments on the device, but the majority got jammed, and I didn't feel great about flying something this sketchy to Mach 2.
That's kind of pathetic. This is not gonna work.
So after testing for a while, I wrapped the section in carbon fiber for extra strength and then turned the camera to point out at the horizon for another onboard shot. I'm actively working on a new camera deployer setup, and you should subscribe if you want to see it in action. For now, we'll have to make peace with how ugly this looks, and with that, let's fly it. We're launching this at the Friends of Amateur Rocketry test site in the Mojave Desert, where I do most of my testing. This place is one of the best resources in the world for experimental rocketry. To start, I want to make sure the rocket still works after the drive, so I slid it down the rail and powered on the flight computer. With the camera deployer out of the picture, the real question for me with this flight was if GPS, telemetry, and roll control would work. The GPS time to first fix was 30 seconds, reaching 10 satellites and a 1.1 meter accuracy within 45 seconds. Really good performance there. Within a minute, we were up to 13 sats and sub-meter reported accuracy, as well as our secondary UGPS online with 10 sats. This is the fancy GPS I mentioned earlier, and I'll be watching the data from this closely. With telemetry and GPS confirmed to be good, I double-checked that the beacon tracker was still working, then drove out to the far gate. It's a little easier to get good telemetry and video from this area, and to be extra careful, I decided to run another set of telemetry and GPS checks with my buddy Charlie helping near the rocket.
Okay, I have my laptop and a telemetry antenna, and the rocket is way off yonder.
I put the telemetry radio on the ground to make the brush interfere with the signal, and despite that, we picked up telemetry within 3 seconds of powering on. Then, just like at the pad, we acquired GPS right away.
We're starting to get some GPS data, but it's not, oh my god, it's accurate. That's 32 seconds to first fix with 7 satellites.
After waiting a little longer for both GPSs to come online, we ran a quick camera test. By 3 minutes, we hadn't dropped a single packet, and we were at 21 and 16 satellites respectively. This is better telemetry and GPS performance than I've had in any rocket ever. So with these checks complete, there's nothing left to do but power on the pad cameras and send it. I'm sorry for what's about to come out of my mouth.
5, 4, 3.
Mach 2, launch on that thing!
Ignition. Ignition.
That's cool.
That was bad.
What do you mean? Did it shred?
Oh, there was a pop.
Okay, we're at...
There's something up there. Something came out.
At this point, the rocket is still in the air, and we're still getting telemetry.
1.3 kilometers.
But do you see this yellow thing? There's only one part of the rocket that's yellow. The parachute. I confirmed this by pointing the beacon tracker at the yellow thing and could hear a faint beeping sound as it drifted away.
Yeah, that's the parachute.
It was hard to tell if the parachute was attached to anything, though. The flight computer was still alive and transmitting data, though some of it isn't trustworthy anymore. The Kalman filter estimating altitude was thrown off by whatever happened in flight, but we were still getting intermittent GPS estimates, and our raw barometric altitude was still showing a speedy fall, which means it probably isn't attached to the parachute. Once the barometric altitude was low enough, signal was lost, and the watchdog timer started climbing up.
All right, so I think that's the last known thing, 20 seconds ago. So it seems like you saw it take a turn?
Yeah, it puffed.
Okay. Yeah, dude, I don't think this thing worked.
We scanned the area with the tracker, but couldn't hear any more beeping, so I plugged in the last known GPS coordinates before it hit the ground. They showed the rocket landing very close to where we were, but I didn't trust these to be accurate. We probably would have heard it hitting the ground if it was that close. Plus, it was going pretty fast on the way down. By integrating the altitude change over the last 10 seconds of telemetry, the rocket hit the ground at about 24 meters per second, 53 miles an hour. That's a hard landing, but it might still be alive, and if we can get a few packets of telemetry, we can probably find it easier. The best way to do that here is to get above the desert brush.
Yeah. I got signal. Okay, I have 15 satellites. We are at a barometric altitude of -7 meters.
The new coordinates were further away, but made much more sense, and with active telemetry packets showing up with satellites reported on the locked GPS, I knew they'd be more trustworthy, so we packed up and went out to find it.
It should be like pretty accurate. Like if you look where your phone location is and you just go right on top of it.
In the next 120 feet.
Oh yeah, look at that.
So it turns out parachutes are entirely unnecessary.
Yeah, I mean the thing I'm learning is why do I put any effort into recovery?
Shout out to Zyla Foxlin for the help with finding this and filming, and it seems like she's right. The upper section of the rocket had slammed into the ground at 50 miles an hour and was still beeping.
It failed on the Kevlar, so this is just a
I
stress.
bet something pushed it apart from the inside. It didn't snap in half.
We can look at the charge, which is very much fired. All right, let's turn this thing off.
With the top half of the rocket recovered, we now have a harder task, which is to recover the booster. This thing fell ballistically without a tracker attached, so we spread out to a wider area to search for it. Since we have this top half though, that means we have onboard cameras and flight data from the computer. So while we look for the booster, let's figure out what happened. Lifting off, the rocket experienced 32 g of acceleration, climbing to a peak of 44. The rocket almost immediately rolls clockwise, which the roll tab tries to correct for, but it isn't powerful enough. The torque that makes the rocket roll is almost certainly the camera bump. The rocket pitched over on liftoff, turning into the relatively high wind on launch day, a phenomenon called weathercocking. A high stability margin can be dangerous on windy days, and as the rocket turns to the side, the airflow pushes down on the asymmetry from the camera bump, creating a much stronger torque than we can really correct for with this tab. The other asymmetries like this enormous hole certainly don't help either, and the rocket ends up in a steady oscillation after the burn. But as we continue, something weird happens with the data. During the burn, our velocity estimate starts to flatten out just past the speed of sound, but it does this while the rocket is reporting an acceleration of over 200 meters per second squared. As the burn continues and then tapers off, the velocity estimate once again goes down close to zero, and at t plus 4.17 seconds, it crosses that line. When it does this, pyro channel 1 flips from a 0 to a 1, activating and sending current into the E-match that fires the parachute deployment charge. 40 milliseconds later, both IMUs go scale high as the rocket deploys parachutes at an estimated 450 meters per second, 1,000 miles an hour. The forces on the chute line ripped the rocket into 3 sections: the chute, the booster, and the upper section. They're all attached to each other by Kevlar lines, but when they rip apart, it happens so fast that it looks like they were never tied together, a thing I know to be untrue because of the camera footage confirming they were tied really well during assembly. Separating the rocket past the speed of sound just tore the lines apart. My favorite way to troubleshoot is to become a 5-year-old who can't stop asking why. I think it's a great way to get to the bottom of things, so let's try it. Why did the rocket separate? It's because the pyrocharge fired. Why did the pyrocharge fire? It's because Ava commanded it to. Why did Ava command it to? Because Ava thought we were at apogee. So now why did Ava think we were at apogee? In Ava's code, the detect apogee function runs after burnout, and it looks for a velocity estimate that drops below 0. The velocity estimate in flight dropped from a positive to a negative number, so now why is that? For a while, this question was hard to answer until I looked closer at where the velocity flattened out. It's just past the speed of sound, so that's probably a clue. Ava's velocity data comes from its Kalman filter, which fuses multiple sensors together in an estimate. To update that estimate, I run an update function with new raw data from each sensor. During flight, I trust some sensors more than others, and sometimes it's better not to run the update at all. I do this with GPS during the boost. It's so unreliable under high acceleration that I simply never allow GPS data to enter the Kalman filter during boost. Similarly, I have a line of code to prevent barometric altitude data from being used past Mach. It's less reliable in that region, so I avoid running the update function with this if statement. I recently started using the barometer to get speed measurements on descent. If we fall from 50 meters to 0 in the last 5 seconds, we must be falling at 10 meters per second, and I let this run slowly at 5-second intervals, adding it to my Kalman updates. So with each update, I'm now providing speed and altitude data from the barometer. The problem is we can't use these speed measurements during boost. They're way too slow, especially in the first 5 seconds where they'll just be 0. So I'll add another condition to this where if we're in the ascent state, we only run that update with altitude and not speed. Then I'll add an else statement so that for every other part of the flight, we'll update altitude and speed. If you haven't caught it yet, the problem is that since this logical AND needs both these conditions to be true, failing either forces us to incorporate those slow speed estimates. So even if we're in boost, if we're also past Mach, we fail this condition and start injecting bad data into the Kalman filter. I wrote this code in a rush to add a little more functionality to Ava a few days before the flight, and this code is what killed it. Past Mach, the Kalman filter started receiving false measurements from the barometer claiming we were going 0 meters per second, but since we were accelerating hard, the filter split the difference and flattened out the velocity estimate. So that's our next answer to the why questions. Is this the end of the investigation though? I mean, we have all our whys, right? Why did Ava command the charge to fire? Because it thought we were at apogee. Why did it think we were at apogee? Because the velocity crossed 0. Why did the velocity estimate cross 0 so early? Because it was forced low by poorly written code with a logical gap. But we're not done. Why was there untested code in Ava's software? Probably because I rushed the build. I had a few logical updates I wanted to make in Ava, and I figured it's just a few if-else statements. What's the worst that could happen? The Kalman filter's pretty robust. You can feed it bad data and get away with it. You just can't feed it untrustworthy data and tell it it's trustworthy. That does not work. The final why is, why did I rush this build? Why did I feel pressure to launch something with 4 days of preparation? I mean, I had the spare parts, I figured I could get it done, but why did I feel compelled to do that? These final why questions don't always have fun answers. Maybe because I had the spare parts already, I felt like the stakes weren't that high if I built a rocket that failed. Maybe, and probably, there's some impulsivity or hubris involved. Maybe I've had a lot of recent success and I kind of figured I could just get away with it. You have enough things that work well and then you just imagine you're immune to failure now. Maybe it's because I named it something super dumb like Mach 2, so right from the start I knew it deserved to die. We found the booster after a fellow rocketeer at FAR mentioned they saw something fall to the north of the site, and after a little walking, it was easy to spot and recover. We weren't the only failure at FAR that day. It's an experimental rocketry facility, so 100% success isn't really the goal. And as long as you're safely in the bunker, trial by fire is a pretty good way to learn, even if it's actually just trial by detonation. With the booster recovered, the upper section accounted for, and a parachute that sailed miles off into the mountains, we wrapped up the day and I resolved to never do a project this dumb again. Probably. Maybe. Right now, I'm working on another version of this camera deployer to get that third-person shot, and I am pulling all of the stops to make it work. It's harder than I thought, but it's going well now, and these behind-the-scenes updates are posted every 2 weeks on the BPS Patreon, and that is how this project is supported. Thanks so much to the patrons who support over there, and thanks to you for watching. My name is Joe Barnard. May your skies be blue, and your winds be low. Goodbye.